Yeah, so I'm Bruno. I'm a postdoc at CCM, and I'm going to introduce wavelet scattering statistics from the perspective of astrophysics. So yeah, these statistics were originally introduced in data science more than a decade ago by many people, so Stefan Malach, Johan Bruna, and collaborators. And the idea was notably to better understand the successes of convolutional neural networks for classification and regression problems. And we all showed that these statistics are also very convenient to summarize some astrophysical data in a meaningful way. And so contrary to neural networks, they don't rely on parameters. It's just numbers you compute on your data. And so the question behind this presentation that we'll try to address is that, yeah, do we need to learn everything when we do use a machine learning method for scientific problems? So I'll try to show you that we don't. Yeah, so yeah, I'll talk about astrophysics mostly, but these kind of statistics have been used in many fields on different kind of data, audio data, medical data, for quantum physics problem, etc. So yeah, I'm sure you will be able to make a parallel for your field. Yeah. So what's the context? So in astrophysics, cosmology, we often face systems that follow a very nonlinear dynamics. So for example, I give here two very different examples. One system which is a large-scale structure of the universe, kind of structure you can see at scales that are beyond the typical scale of a galaxy or a cluster of galaxies. The way we understand the origin of this structure is that it's shaped by the evolution of a dark matter fluid, which evolved gravitationally in an expanding universe. And what really makes the understanding of this large-scale structure complicated is that there are some nonlinearities. We know that scales are coupled in some way. Same for a very different context. When you study the interstellar medium, the medium between stars of our own galaxy or of different galaxies, you basically have a fluid, a magnetized fluid made of gas and dust, which is highly turbulent and that, again, follow a very nonlinear dynamics. So in all of this, what's really important is that the fact that you have these scales that talk to each other. So if you want to describe from a statistical perspective this kind of data, you have to pay attention to that. From a statistical point of view, often you will have non-Gaussian statistics because of this nonlinearity. So yeah, so this is a question we all face, right? We have some data. We want to understand what really matters in this data. And so there is this fundamental question about, OK, how do we describe this? So at some point, we need to build relevant features, summary statistics, or representation. Like I use these words in like very equivalent way. So if you want to describe this kind of data from a statistical point of view, you will use statistical descriptor. You will use the mean, the variance of your field. You might use a power spectrum, which is a statistic very used in cosmology that tells you how much power you have at a given scale. And you may use a more complicated statistics, the bispectrum, that tells you a bit about these couplings between scales in your data. But you have to make some choices. And you usually also want to leverage the symmetries, the invariance of your data. You want to define descriptors that understand these kind of ideas in your data. OK. So when you have non-Gaussian statistics, obviously you cannot use a Gaussian model to describe your data. And this is an illustration of that. Here, so if you assume that you have some data that is statistically homogeneous, you know that a Gaussian description of this data will be entirely characterized by the power spectrum. And so I show you an example here of Gaussian model of this data on the left. And you have a sample on the right of this Gaussian model. So both images share the same power spectrum. So they have the same power at each scale, but they don't take into account the couplings between scales. And you see that the impact of this is that you have completely different features. And so, yeah, it seems reasonable to go beyond this power spectrum description if you want to understand this. So yeah, we're on a meeting on machine learning, so I'm going to talk a bit about machine learning. So how machine learning addresses this problem of building representation from the data. So somehow, if you want to solve an inference problem, a classification problem, do generative modeling, at some point, you have to learn a representation of your data. But it's learned from examples. So you need to give examples, train some loss function, etc. And in the end, you automatically extract what matters to make a prediction, to solve inference or other kind of problems. So here I'm showing you an example of convolutional neural network that was it's a LeNet CNN, which was designed to classify digits in images. And the first part of the network is really about building this representation phi of an input x. Once you have this representation, then you make a prediction. So this kind of approaches work very well, but for the problems we have is that they require examples. We need to learn it somehow. And the features, the representation that is extracted from the data is not easily interpretable, or even most of the time it's not interpretable at all. And so it's kind of a problem when you do science, because you want to understand what you do to make a prediction, right? And it's also quite a problem for specifically to astrophysics and cosmology, because often you see one sky, you see one example of the data you really care about, and so you cannot train on observation your data. You have to use simulation in some way. So it's a problem. So the wavelet scattering statistics are quite you can see that in an alternative way to build representation. So it's a predefined representation of your data, if you want. So I'm going to talk first about the wavelet scattering transform, which is one class of wavelet scattering statistics. So it's built on a multi-scale representation of your data, meaning that it first decomposes your data on wavelets, which typically look like this on images. Like the idea is just to decompose your data on things you can understand locally, like just decompose your data on oriented scale. And so you do that by convolving with wavelet filters, which are just bandfast filters, which typically look like this. So here it's an oriented wavelet parameterized by its extent j and its angle theta. And the wavelet scattering transform is built in a sort of similar way to what's happening in the CNN, but it doesn't involve any filters, learnable parameters, learnable filters. It basically replaces the learnable filters by wavelets, in simplified version. So it's a cascade of operation involving the wavelet transform, nonlinearity, which is not a ReLU here, but just a modulus. And you have average operator, spatial average operator, which define coefficients from your data. So typically, can I use that? Yeah. So you can compute you compute coefficient at each layer of operation you make on your input x. So you can compute just the mean of your field x. But you can also compute the S1 coefficient that will be the mean of the modulus of the wavelet transform of your signal, or S2 coefficient that will involve two successive convolutions with wavelets. So you can do that as you want. But what's really interesting is that this S2 coefficient will first quantify this interaction between scales. And actually, we will have some set of coefficients that will describe your data in a sort of way you can understand. So it's quite of similar in terms of structure with CNN. It's not exactly the same structure, but there is no learning step. So to be more visual, this is how the wavelet transform looks like when you apply it to some data. You have an image on top left on which we compute the wavelet transform on top right. And so you see that the wavelet transform is really about selecting the spectral content of your image at a given oriented scale. And so it's a local decomposition, and you see at the bottom the Fourier vision of what we are doing, like it's bandpass filtering, so you just select the spectral content. And so the wavelet scattering transform is about doing this kind of operation several times with a modulus in the middle. And so in the end, you end up with this kind of coefficient. You usually go to S2 coefficient only because beyond there's not much you have to capture within your data. So this is one way to define a representation that doesn't involve any learning, and it's quite interesting because it can quantify the non-Gaussian properties of your data. But it's not the only way to do that, right? You have another set of statistics that were more recently introduced by Stefan Mala and collaborators, which rely on on computing covariances between your data filtered at different scales. Again, the idea is to quantify these couplings between scales. The natural way to do that is to compute a covariance. But the problem is that when you filter your signal at different scales, then the covariance will be systematically 0 if you don't do anything more than that, because the phase maps are not coherent. And so to address this issue and define numbers that really tells you something about interaction between scale, you need to add a nonlinearity. And this nonlinearity here is called the phase harmonics, which is defined on the top right. So it's a pointwise operation where you take your pixel and you accelerate the phase by the given factor p that helps you to make your phase map consistent and capture this kind of correlation between scales. So this is what I wanted to tell you about the statistics. And so now I'm going to talk a bit about application for astrophysics. So we have a way to quantify the non-Gaussian properties of our data. And it's first important just to describe, as I told you, your data. You can make quantitative comparison with different maps if you want to compare observation or compare observation to simulation. And what is kind of interesting also is that you can really leverage the group of symmetries of your problem related to your problem because you using like really things that you understand, like the wavelet transform, non-linearities, etc., or cascade of operations like that. And so you can really compare your data in a sort of exhaustive and meaningful way. And so this is what we had used to describe the interstellar medium with a group of people, including Erwan Alice, François Huvrier, François Boulanger, a couple of years ago. You can use that also to make classifications. And so this was used by Andrew Sajari and a collaborator, not part of this work, but I feel it's like super interesting because they make a classification on like data that can have that come from different kind of numerical simulation, magneto-hydrodynamic simulation with different Mach numbers, and like they show that they can distinguish very easily this different kind of simulation based on the scattering statistics. So also used on inference problem. It was used on weak lensing data by Xiao Cheng, Brice Ménard, and collaborators, and they were able to show that they could constrain cosmological parameters in a sort of way that was as good almost as a CNN approaches involving parameters. More recently, we have been working with Michael Eichenberg, Cheng Hunan, and Shirley Ho and collaborators on using this kind of description to do simulation-based inference of cosmological parameters on galaxy catalogs, so 3D data. You have a point cloud where every point is a galaxy. You want to make measurement on the spatial distribution of this point cloud and get information on a set of parameters that tell you something about the evolution of the universe. And so we were able to show, I mean, we're going to publish a paper soon on that, but we were able to show that using scattering statistics on this kind of point cloud helps us to constrain the cosmological parameters in a better way than power spectrum statistics, which have been used for a long time already on this kind of data. And so this kind of approaches helps us to use the fact that there is some information, non-Gaussian information, that we can use to constrain cosmological parameters in this kind of data. So this was an example to describe your data, but this kind of statistics also helps you to define generative models. And what is quite interesting is that you can define generative models from a single example of your data. This relies on maximum entropy models, which are a set of models that are basically models with maximum entropy on a set of data Y that are sufficiently close in terms of statistics to the target X. And so these kind of models are just telling you that you define the most general way to describe your data that is constrained to respect a certain set of statistics. One way to, I mean, it's not super easy to sample this kind of maximum entropy model, so we have to use approximation to do that. And the way we do that is just minimizing this kind of loss function starting from a white noise. So you start with a white noise, which is a process with super high entropy, and then you basically follow a gradient descent on this kind of loss that helps to build a map that matches the statistics that you want, phi of x. And if you use this kind of models using wavelet phase harmonics statistics, so this is phi of x, then you can make realistic samples of realistic models of your data. So here I'm showing you an example of samples built from a generative model solely based on the original map on the left. And it was a work led by Erwan Alice, Tanguy Marchand, and collaborators. And they were able to show that, first visually, that the samples look realistic to describe what's happening and to capture the statistical properties of the original map. And quantitatively, also, they were able to show that the pi spectrum, the power spectrum, histogram, like a lot of statistics were conserved by this kind of approaches. So more recently, with collaborators, we had generalized these kind of models to multi-channel data, multi-channel images. So you see an example on the top of dust emission maps in total intensity and polarization. So you have 3 maps that describe this medium. And we built generative models of this kind of data only based on the original maps on top. And you see an example of realization at the bottom of the maximum entropy model based on the wavelet phase harmonic statistics. So yeah, the interest of this generative model is that first it gives you a way to sort of quantify the exhaustiveness of your set of statistics. How much do you have? Do you capture with your set of statistics? And is this enough to fully describe what you want to describe? And also, it can be used in different contexts. We've used it to do forward modeling of a mixture of cosmic microwave background and dust emission maps. And so we had done simulation-based inference in a work led by Naya Jeffrey based on mixture of CMB and dust. And the model of dust was a generative model based on only a single example of dust emission maps. And you can see the result of the source separation on the right. So yeah, this is the interest of this model for generative modeling. And so also I wanted to talk about the interest of this statistics for statistical component separation, which is some term I will explain. So for source separation problem, typically you want to recover a signal x naught from a mixture, linear mixture, y equal x naught plus epsilon naught, where epsilon naught is a contaminant. And but in many situations in astrophysics and cosmology, you don't really want x naught. You want some property related to x naught, phi of x naught, and which can be a set of statistical descriptors, for example. And so this is what the statistical component separation problem addresses, recovering this phi of x naught given y. And so to do that, we had introduced a couple of years ago an algorithm consisting in minimizing this kind of loss function starting from y. So you progressively deform your observation y to make a map such that this map plus sample of your contaminant will match your observation y. So we have we had used that on astrophysical data a couple of years ago, and we have spent some time with Michael Kuenberg to sort of better understand the mathematical properties of this algorithm recently in a paper that will be out soon. And yeah, I'm just going to show an illustration of the interest of this. So we had used this kind of techniques to do denoising with a complex instrumental noise. And more recently, Constant Auclair and collaborators have used this to separate dust emission maps from a cosmic infrared background observation. And I'm showing you the visual results, but we can show that we can recover some non-Gaussian properties of each of the components. OK, so I'm a bit late. We'll just conclude here. So yeah, I presented this wavelet scattering statistics, so namely here the scantrix transform and phase harmonic, but there are other ways you can define a similar kind of statistics that really focus on capturing interaction between scale. And it's a sort of way to represent your non-Gaussian physical field. So there is no learning. You can use it on a single example. It helps you to have a better interpretability of what you do, because these are operations you understand. And yeah, it can help you to describe models, separate fields. And so if you want to try this on your data, on images, I've made some packages to work with the scattering transform, phase harmonics, but there are also other tools to do that. But anyway, I would be happy to discuss with you if you feel it might be interesting for your field. So thank you very much for your attention, and sorry for the couple minutes late.
Any question for Bruno?
So these parameters, theta, that you have in your wavelets, how do you select it in practice?
The parameters,
Theta.
Theta.
The angle of the...
Oh, the orientation. So usually you... so I'm going to maybe show a picture of this. Yeah, so the way we do that is that we first start with a collection of wavelets that allow you to probe every oriented scale in your data. So you make sure that you have some discretization for J and theta that cover the whole Fourier space to decompose in a reversible way if you want your data.
Okay, and this method of scale invariance with the wavelet scattering, so I can use it like in every type of data that is in a sense scale invariant, like the Ising model or this type of stuff, like that is like.
Oh, you don't need a scale invariance, so
okay.
you can
sorry, I mean the generative modeling.
Yeah. So for the generative models, one important assumption of this is that you have to have statistical homogeneity and ergodicity of the process you want to model, and but there are some ways to make without it. Yeah, so, and for the scale invariance, you can quantify whether your data is scale invariant or not, or leverage the scale invariance to simplify your description if you want, but you don't need scale invariance to do that. You can apply it to non-scale invariance.
Okay, so this generative modeling technique is really like for when you have very few images that have a specific property of scale invariance. But for instance, if I have one picture of a dog, I could not use this method, for instance, to generate picture of dogs, right?
In that case, no, because you need like this statistical homogeneity assumption.
Okay.
And so it's more for data that looks like texture. You know, like you can see that in a lot of scientific fields. And so, but for natural images, it's more complicated. And so you cannot use directly this kind of statistic, but with a set of, if people have mixed parameters and like learnable parameters and this kind of statistics to address classification problem on natural images, and so but you need to go a bit beyond that if you want to.
Any other questions for Bruno?
So it sounds like you're really asking a different question, because when I think of, like
someone's
vision
thinking on Zoom.
classification.
We can't really hear the question on Zoom. Can AV tune up the volume a little bit?
Can you use your seat mic, please?
Can you increase the volume of like whoever's speaking on Zoom? Because it's a little bit soft. We can't really hear. Someone's asking a question on Zoom.
Okay,
Right?
yes. Can you hear me now?
It's not amplified.
It's not amplify. If you can tune up the volume for.
You have to push the black button down, and then the microphone will pop up. The podium mic is on.
Someone's on Zoom saying something. Yeah, right. Okay. Can someone on like the person on Zoom say it again?
Hello, can you hear me?
We'll repeat the. Yeah, people can hear you. We'll repeat the question if it's not clear.
Okay, yeah, the question is, it seems like you're asking a different question, because when I think of vision systems, it's like you give it a picture of an animal and it tells you whether it's a dog, a cat, or a cow. And you just said you can't do that. So what is the question you're solving exactly? Right? Was that first of all, is the first part correct? You can't tell the difference between a cow and a cat using this method?
Well, it's not perfectly suited to this kind of data out of the box, I'd say, because here I'm notably defining coefficient that assume statistical invariance, statistical homogeneity of the data, and so I mean images of cats and dogs don't fully follow this kind of assumptions, and so yeah, the idea of this kind of statistics is to represent data that is usually statistically homogeneous in a way that rely on capturing interaction between scales or properties or sparsity of the data, and so I'd say the goals are to use it in more scientific context where it makes sense to talk about interaction between scales and rather than on working on images of cats and dogs, if it answers the question.